أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم. Today we'll be talking about bipolar junction transistor circuit analysis. This lecture is a part of series of lectures regarding the course of Introductory Electronics having the course code of PHY 201. In today's lecture, basically we will try to understand the circuit analysis of bipolar junction transistors. We will also move toward the understanding of collector characteristic curves, and at the end of this lecture we will discuss the different modes of BJT, that how we can use the BJT as a switch, as a amplifier, or as in saturation modes or in different modes. So first of all, we would like to know about the BJT circuit analysis. There are some terms or some voltages or the notation that need to be understood before moving toward the BJT circuit analysis. So if we look toward the BJT circuit analysis, then it is very clear that there are three DC voltages and three DC currents which we need to be considered, and the measurement of these factors are important for the troubleshooting of the systems. So the three different currents are the first of all is the base current, that is represented by AB, and this is called as a DC base current. IE actually represents the DC emitter current, that is represented by IE, and the DC collector current is represented by IC. Here if you look in these figures, this is IC, that is actually the collector current, this is IE, that is actually the emitter current, and this is IB, that is actually the base current. Coming toward the DC voltages, we have the first DC voltage, that is called as VBE. This is called a DC voltage across the base emitter junction. If we look towards here in this figure, then this is actually VBE, that is actually the base emitter voltage, and we have VCB, that is actually the voltage, DC voltage, that is across the collector base junction. This is the DC voltage across the collector base junction. This is actually called as VCB. This here, this is VBE, and the third one is the DC voltage from collector to emitter, that is represented over here by the red color, and that is VCE, that shows the DC voltage from collector to emitter. Now coming towards the base emitter junction, when this is in the biasing mode, in the forward biasing mode, so what will happen and how we can calculate the values of the current or some unknown quantities. So coming towards the base, when the voltage BE, that is base emitter voltage, that is 0.7 volt, so what happened, we have the simple equation that VRB should be equal to IB into RB, that is by Ohm law. So if we put this value over here, so we can get something from here, that substituting the value of VRB, we can get that IBRB, it should be equal to VBB minus VBE. And after solving this equation for IB, we can get a very simple equation for IB, that the base current should be equal to VBB minus VBE divided by total divided by RB. So if you want to calculate the voltage at the collector with respect to the grounded emitter, then we have the simple equation for that, the voltage of collector emitter junction is equal to VCC minus VRC RE, and similarly if we apply the Ohm law, then VRC should be equal to ICRC, and the same equation for the voltage at the collector with respect to emitter should be like VCE should be equal to VCC minus ICRC. So this is actually the voltage across the reverse bias collector base junction. This is actually the calculation if some problems is given to us and there are some unknown quantities among these equations, so we can easily find out the unknown quantity by using these equations. So now we are coming toward the collector characteristic curves. That what type of characteristic curve we will have for collectors. So if we have a graphical illustration of the relationship of a collector current and the VC, the voltage, that is actually the collector emitter voltage, which is called as a VCE, with specified amount of base currents would happen. So with greater increase of VCC, that is actually the external potential difference, the VCE, that is actually the voltage across the collector emitter junction, that continues to increase until it reaches the breakdown region. We have a breakdown regions, but the current remains about the same in the linear regions, that is actually from 0.7 volt to the breakdown limit. So this curves, that is actually the set of curves that could be easily drawn here. We have this set of curves. This is actually called as a collector characteristic curve. If we look toward this equation, this will start to move, from 0.7 volt, that is actually the B point across this curve, and similarly we have a C point across the curve, that is actually VCE. So we have set of curves like this that could be drawn for the different values, and that is actually the family of IC, that is actually the collector current, versus the VCE, that is actually the voltage across the collector emitting junction curves for several values of IB. So I mean, if we are changing the value of base current, we will have different set of collector curves, collector characteristic curves for that. Like here we have for base current of IB is equal to 0, we have this curve, and for other base current just like IB1, IB2, IB3, or maybe several IB that have different values, we have this characteristic curves for the collector characteristic curve for this collector to collector current versus the collector emission voltage. So we want to solve a very simple example regarding this collector characteristic curves, and we need to draw that. So we will have, we will solve some very simple problem on that for a type of practice on the problems. So this is a very simple problem in which you need to draw an ideal family of collector curves for the circuit in this figure. For this case, the base current is given to us, and it is from base current, that is actually 5 microampere to 25 microampere, and there is a gradual increase in that, and the increment of increase for this particular case is 5. So this means we need to draw the curves for the base current, where we have the base current value 5 microampere, 10 microampere, and 15 microampere, 20 microampere, and finally 25 microamperes, and we need to sketch the collector curves for that. And for this particular case, we need to assume that beta DC should be equal to 100, and the VCE does not exceed the breakdown limit. So this is some sort of boundary condition for that, for solving this family of curves. So this is a simple diagram for this. We need to solve this problem in the upcoming slide. So this is actually the solution of the previous problem what we had discussed in the last slide. So we need to draw the ideal family of collector curves for the circuit, and the values for the base current should be here, that is mentioned here: 5 microampere, 10 microampere, 15 microampere, and 20 microampere, and finally 25 microampere. So what sort of collector characteristic curve we should have for this particular system? Keep in mind, on the vertical axis we have the collector current, that is measured in the value of milliampere, and in the horizontal axis we have VCE, that is actually the voltage, and this is the minimum voltage what we need for the creation of this curves, that is actually 0.7 volt. Here it is mentioned there. This is the circuit diagram for this. The beta DC is also already mentioned, that is equal to 100, and the VBB and VCC are already clear. So if you want to measure the collector current with respect to that, Then for 5 microampere collector base current, we will have 0.5 milliampere collector current, and similarly for 10 there should be 1 milliampere, and for 15 microampere there should be 1.5 milliampere collector current, and for the 20 microampere base current there should be 2.0 milliampere collector current, and finally for 25 microampere of the base current we will have 2.5 milliampere of the collector current. This is actually the simple explanation and understanding of the simple problem in this slide. So we are coming toward the different modes of the bipolar junction transistors, that how we can use this bipolar junction transistor as a switch, or maybe in cutoff mode and in saturation mode, or maybe in running mode. So we are coming towards the simple mode, that is actually the cutoff mode. In the case of cutoff mode, is actually specified it is the mode when there is no base current. So the transistor in this case is in cutoff region, and just as the name implies, because it's very clear from its names, there is practically no current flows in the collector part of the circuit. So that is the simple explanation for that. So with the transistor in a cutoff state, the full VCC can be measured across the collector and emitter, so that is actually VCE. So it is simple explanation of this cutoff mode, where there is almost practically no current in the collector part of this BJT. So the collector leakage current, that is actually called as a ICEO. This is called as collector leakage current, is extremely small, and that is usually neglected. The magnitude of the collector leakage current is very, very small, and that is normally considered, and then that is ignored. So based on if we look toward the base emitter and the base collector junction that are reverse bias in this configuration, looking toward the base emitter and the base looking toward the base emitter and base collector junctions, it is clear that it is reverse bias. So that is why the system is the BJT is working in cutoff mode, and there is no current across the collector. We are coming towards the saturation mode of this BJT. How this BJT can be used in saturation mode, where it can have a type of maximum value for if we look when the value of VCE that reaches to the maximum value, so what happen, the transistors comes across the saturation region. So what is actually the saturation region? Normally if we look toward the normal phenomena, with increasing IB due to the VBB, that is external potential difference, the collector current increases. When we increase the base current, would happen due to the increase in base current. Keep in mind the base current could be increased with the help of VBB, and if we increase the base current with the help of VBB, would happen, the collector current also increases, and VCE decreases due to the increased voltage drop across resistors across RC. So when the transistor reaches saturation, that is actually IC can increase no further regardless of further increase in it. That is actually a type of direct proportionality. Increasing the value of IB can lead to increase in the value of IC, but a time reaches where further increase in IB could not further increase the magnitude of IC. So what is that particular case? This is considered to be the saturation mode. The IC can increase no further regardless of further increase in IB. Increasing IB would not affect or would not further increase the magnitude of IC. So this is, in this case, base emitter and base collector junctions are forward bias. So this particular mode when no increase in IC could be found with increasing the value of IB, it is called as a saturation mode of the BJT. And what is the basic requirement for this mode? For this mode, the base emitter and the base collector junction should be forward bias. So we have DC load line for this particular case, where we want to graphically illustrate the magnitude of saturation current, that is for the collector current, and the cutoff mode of the transistors, that at which point there will be cutoff mode and at which point we will have saturation or the maximum current that is possible. So here is the red color actually shows this is the saturation mode, where we have maximum current and the saturation current across the vertical axis. Here IC represent the saturation current, and on the horizontal axis we have VCC. This is actually the cutoff mode, where when there is no collector current, I mean if we look towards, if we draw a projection across the vertical axis, then its values comes to be 0. So this means that at this particular point there is no collector current. So that is why this mode is considered to be the cutoff mode. So the active region of the transistor operation is actually that's specified by this DC load line. So DC load line actually specifies or it is specified in a family of collector characteristic curves, and it illustrates, clarify the cutoff and the saturation modes of these transistors. So we need to solve some problems, very easy problems based on this cutoff and saturation mode. Some value is given to us, we need to solve the unknown value, or we need to find out the unknown values from the equation what we had developed on the second slide of these lectures. So a problem is given to us, we need to determine whether or not the transistor in figure is in saturation mode, and in this case the voltage VCE what we need to take is VC is equal to 0.2 volt. So here is the VBB, the magnitude of VBB is 3 volt, and this is 0.2 volt, this is 0.2 volt, and this is VBB is 3 volt, and the resistance, that is actually the RB for this particular case, is 10 k ohm, and for RC is 1.0 k ohm, and for beta DC is equal to 50, that is actually the ratio. The magnitude of VCC is 10 volt. So what we need to calculate, we need to determine whether the transistor in this particular system is in saturation mode or not. So first we need to determine the value of collector current, and that is very easy to measure. The magnitude of collector current at the saturation point is equal to VCC minus VCE at the saturation, that divided by RC. If you put the value across these equations, what happen? 10 volt minus 0.2 volt divided by 1.0 k ohm. So that is after simplification of it, we can get the value of 9.8 milliampere. So now we look toward the base current. So we want to measure the magnitude of base current, and we want to know that whether the base current is large enough to produce the saturation collector current. So the equation for the base current is very simple, and that is equal to base current IB is equal to VBB minus VBE divided by RB, and that should be equal to 3 minus 0.7 divided by k ohm. And after simplification we can get the value of IB, that should be equal to 0.23 milliampere. And now we can come across the IC, that is equal to beta DC IB. So we can do the simple multiplication from that, and from that we can get the collector current, that is equal to 11.5 milliampere. So this is the simple solution for that. And the IC greater than, here if we look toward that, the collector current, that is IC, it is greater than IC saturation. So therefore the transistor is saturated. This means the transistor is saturated if we get the value of IC, that is almost 11.5 milliampere, and the value of IC that is given to us, that what we have calculated, that IC saturation, it is equal to 9.8 milliampere. So from this we can assume that it is in saturation mode. we have maximum transistor rating when the transistor has limitation on its operations, and in this particular case the product of VCE and IC cannot be maximum at the same time. So if VCE is maximum, IC can be calculated as that is for a simple equation that the collector current should be equal to P into D maximum divided by IC. And on this equation we can solve a very simple problem. When a particular transistor that should be operated with the VCE is equal to 6 volt, and if its maximum power rating is 250 milliwatts, what will be the most collector current that is it can handle. So we can get from this simple equation this above what we had developed just before, that is from the maximum transistor rating. So putting the value of these known values, we can find out the unknown quantities. So 250 milliwatt divided by 6 volt, that should be equal to 41.7 milliampere. So this is something about the circuit use of BJT transistor. In the upcoming lecture, I hope inshallah we will discuss Allah.